If I could have your attention, I think we're ready to start our program with Carl this evening. Carl Waltz is an astronaut, has flown a number of times and flew on the International Space Station. And he is now working at NASA headquarters, and hopefully he'll come back to Houston someday. But let me turn it over to Carl.
Thank you, sir. Well, thank you very much. It's a pleasure to be here today. It's really neat when I walk into a conference like this, and I know so many of the people, and so it's like an old home week. And since I am I think still a laboratory specimen, it's neat to be able to be here and to talk about these issues, because they're very important to all the crew members that are out there. Our health, our safety, these are things that are certainly important to our families, certainly important to us, and we trust you all to do the right things to make sure that we're safe when we fly on the shuttle, on the station, and certainly on the vehicles that I'll be showing you today. Now, I get to do the talk that Doc wanted to do this morning, but with all the flashy videos. But he wasn't going to be able to show all the the cool videos anyway. So in their entire length. So this is my first foray into embedded video into PowerPoint. But we've looked at it, and it appeared to work okay here. So I'm very excited about this. And so. What our current plans, of course, I think you all are familiar. It's the Ares run with the Orion, leading to the Ares 5. Before that, of course, we have our lunar precursors, and so you'll see those in the talk. So I'd like to thank Mr. Abbey and Dr. Alford for inviting me to come down and give this presentation today. So just sort of to lay the groundwork, I'd like to talk a little bit about the NASA mission directorates, because we're very familiar with some of them, but as I discuss, we'll see that they're all working together toward the vision for space exploration. Now, space operations, Bill Gerstenmaier, who you heard at lunch, is the associate administrator for space operations, and they provide the agency with the leadership and management of NASA's space operations, the shuttle, the station, and also very important, the space communications element of our NASA activities. So that's our space operations. Now, when we go to our Science Mission Directorate, the Science Mission Directorate engages the nation's science community, sponsors scientific research, and develops and deploys satellites and probes in collaboration with NASA's partners around the world, and looking at the Earth, looking at the planets, and then looking beyond at the cosmos. And I failed to mention also, of course, in the space operations, that we work very closely with our partners. And you'll see partnership comes up quite a bit. The Aeronautics Mission Directorate is the leading government agency engaged in aeronautical research. And our world-class capability is built on a tradition of expertise in aeronautical engineering and its core research areas. So they have been, of course, that was before there was NASA, there was NACA, and NACA encompassed the aeronautics research. Now, the new organization is the Exploration Systems Mission Directorate that Scott Horowitz leads, and I work for Scott. And of course, we're involved in accomplishing the vision for space exploration, seeking to answer fundamental questions about our existence, responding to recent discoveries, and putting in place revolutionary technologies and capabilities to inspire our next generation, the world, and the next generation. And what we try to do is to collaborate with space operations, with science, with aeronautics, to develop the new vehicles and systems that we'll be using to send humans to low Earth orbit, to the moon, and beyond. So the vision for space exploration, of course, gave us our new path. And some of the path was the same path, was to complete the International Space Station, safely fly the space shuttle, although with the plan to retire the space shuttle in 2010. And then to develop the new crew exploration vehicle, now called the Orion, in 2014. And with the idea to return to the moon in 2020. Eventually expending human presence beyond low Earth orbit, beyond the cislunar space, to the solar system and beyond. Implementing a sustained and affordable human and robotic program, developing, supporting innovative technologies, and promoting international and commercial participation in exploration. Now, in my talk, we'll talk about why we're going to the moon. We'll discuss how we plan to get there, and that's where we have the cool videos of the rockets. What are our technical challenges? And many of those technical challenges are challenges that we've discussed today in our meetings. And then to talk a little bit also about the role of our robotic missions. And I have some video to show you what we plan to do with our lunar robotic program. So the vision for space exploration leverages the historic legacy of our Apollo program. And of course, we were very fortunate to have 12 astronauts to land on the moon. They landed in many different areas, and that was quite a while ago. The last person to leave the moon was back in 1972, and we've really only scratched the surface as far as understanding what the history and the scientific significance of the moon. Now, along with the vision for space exploration, we are in the process of developing a global exploration strategy. And we have reached out to our partners, and through a number of meetings in 2006, we developed 6 exploration themes. Human civilization, to extend the human presence to the moon and enable eventual settlement. Scientific knowledge, pursuing scientific activities that address the fundamental questions about Earth, the solar system, and the universe. Preparation for exploration, to use the moon as a test bed to test technology, systems, flight operations, and exploration techniques to reduce the risk and increase the productivity of future missions to the moon, to Mars, and beyond. Global partnerships, again, providing a challenging, shared, peaceful activity, leveraging the work that we're doing on the International Space Station. And then also the work that we're doing internationally with the scientific community and the Science Mission Directorate. Economic expansion. What was very interesting when I had an opportunity to go to Jamestown, and the exploration of the New World was driven by economics, and so one of the ideas, one of these global themes, was to look at what kind of opportunities are there for economic expansion on the moon. And then finally, public engagement. Again, using a vibrant space exploration program to engage the public, encourage students, and help develop the future workforce that will be required to address challenges of tomorrow. And I know that in our joint working group in Moscow in November, we talked with Dr. Grigoriev about that issue in Russia as well as in the United States. So this is an issue not just of America, but a global issue. So what I'd like to do is to play this video that illustrates the global strategy and talks a little bit about lunar exploration.
Looking up into the night sky, the moon is 240,000 miles away. It seems almost close enough to touch. From our vantage point, we observe only one side of the moon, the side on which 12 American astronauts walked almost 40 years ago. The side facing away from Earth has been viewed only by a few orbiting spacecraft. Neither robots nor humans have ever touched this surface. If current theories are correct, the moon broke away from Earth about 4.5 billion years ago and cooled, forming a time capsule of early Earth. This record has been lost to us because of the constant renewal of the Earth's surface. Without a protective atmosphere, meteorites and comets have bombarded the lunar surface, sculpting a dramatic landscape. The Aitken Basin, located near the moon's south pole, is more than 1,000 miles in diameter, making it the largest known impact crater in the entire solar system. To study the lunar terrain and learn its secrets, robots and human explorers will need to analyze the surface over many years, establishing the first highly self-sufficient human presence on another world. Replenishment of food, water, air, and other supplies will be required to sustain human activity on the moon. In some cases, local resources may be used to augment recycling. For example, extraction of oxygen from the lunar regolith can provide air for crew facilities or propellant for future space travel. Future analysis will determine if water has been deposited by cometary bombardment. Some scientists believe that this material may be buried in permanently shadowed craters and frozen in place by the extreme cold. Today, 80 nations are involved in space activities. The International Space Station represents the achievements of a complex partnership among 5 space agencies. By watching in real time as space explorers solve difficult problems in math, engineering, and science, young people will be encouraged to learn more about these challenging subjects. New opportunities for cooperation will build strong global partnerships that serve as the cornerstone of our future efforts to overcome the challenges of voyaging to destinations beyond. Future exploration beyond the moon will include round-trip voyages that last for years in reduced gravity and with exposure to high radiation. Mars-bound astronauts will be totally independent from Earth. In preparation for these future voyages, each robotic mission in NASA's Mars exploration program is producing new discoveries.
So we hope that as we explore, we can answer some of these compelling scientific questions, characterizing the moon's atmosphere to better understand the surface boundary exospheres, to characterize impacting craters over the moon's geologic history, trying to understand that early solar system history, to study the lunar regolith, understand the nature and history of solar emissions, galactic cosmic rays, the local interstellar medium, and to determine the origin and distribution of lunar volatiles, to support studies of the origin, composition and structure of the moon, and in doing so understand other planetary bodies. Now, as we develop our new series of rockets, we hope to leverage the work that we have done in the past with our Saturn V and with our space shuttle. This is a deceiving number. This 20 metric tons, actually, when you consider the space shuttle takes itself up and down, it's much more like 120 metric tons of launch capability. Then taking the best of these two rockets to develop our Ares 1, which is an extended a solid rocket motor with an upper stage using the J2 engine from the Saturn V, and then eventually Ares 5 utilizing two of these 5-segment solid rocket boosters with the RS-68 engine currently used on the Delta IV Heavy, and also an upper stage utilizing the J2. So building off of our legacy systems and then bringing them to develop new capabilities. Now, our exploration roadmap gives an idea of how we plan to develop the new capabilities, both the development of the initial Orion capability, preceded by our lunar robotic precursor missions, and along this line, the continuation of our science missions to Mars. Along the way, we have a new segment, the commercial orbital transportation system, where we have actually incentivized private industry to go out and develop a capability to take humans and cargo to low Earth orbit. So that is in the works as well. Of course, we have the shuttle operations, which will end sometime in 2010. Orion development moving along, eventually leading to a capability in the 2014-2015 timeframe. And, of course, Ares going right along with the Orion. Eventually, we plan to develop the lunar lander, and in fact, we are starting the initial conceptual designs of that lunar lander. We're looking at technologies that we might need for that, and also for the surface systems that we would need as well. And then, again, we'll leverage off of Ares 1 as we develop the Ares 5 launcher. So all in all, we have a lot of things in work right now to try to get eventually to humans on the moon in the 2020 timeframe, as the vision sort of laid out for us. Now, what I'd like to do is to illustrate this with another video of how we propose to go to the moon, and this will have the launches of the vehicles, the Ares 5 and the Ares 1. Now, this will be on one of the modified pads that we currently use for the space shuttle, the Complex 39 at Kennedy Space Center. Orbit for what is the translunar injection stage and the lander. Now, in contrast to Apollo, we will launch the crew separately on an Ares 1. here's the launch of the Ares 1. Again, the 5-segment solid rocket booster. As it burns out, then the second stage will take the Orion capsule into low Earth orbit, and then the Orion capsule and its service module separate, and then will link up with the previously launched lander and the translunar injection stage. Once the docking is achieved, the Earth departure stage will fire and take the lander and Orion, put them on their way to the moon. Eventually, the engines on the lander will fire to capture the lander and Orion into lunar orbit. And eventually the lander will separate. And will land on the surface of the moon. Our lunar architecture team, after long deliberations, decided that we should aim toward developing an outpost, and so we will plan to try to leave as much infrastructure as we can with each landing on the moon, and try to land several times together and be able to bring those units together. And of course, here's the Orion returning to Earth. Making a parachute landing on the back, probably in the western United States. Right now, our concepts look toward using airbags to help cushion that landing shock. So we have a lot of technical challenges to achieve this this kind of mission. So we need to test technology, systems, flight operations, and exploration techniques to reduce risk and increase the productivity of the future missions, not only to the moon, but to Mars and beyond. So from the technology and the research community, we need to support the development of the technologies needed for the lunar lander, such as ascent, descent engines, guidance systems, payload capabilities, to develop a robust EVA capability, demonstrate effective closed-loop life support systems, demonstrate the potential for in-situ resource utilization, to understand the effects of the integrated human and lunar environment on human performance, to deploy effective on-site remote healthcare systems to ensure crew health on the moon, and then to develop high-resolution topographic maps of the lunar surface. So it's a tall order, and we've already started to look at some of these needs here. So we've talked a little bit about the lunar lander habitat, and as I've mentioned, we've started early design work on that here at Johnson Space Center. As part of the Constellation program, Lori Hansen is looking at different configurations for the lander. There are a number of trade studies that are out there looking at the propulsion systems. From the technology area, we have started doing testing on a throttleable RL-10 engine. It's a liquid hydrogen, liquid oxygen engine that we think could be one of the engines that could be used on a lunar lander. And we've had very good success in throttling down from 100% down to 10%, which is something that had not been done before. And we've learned a lot about what happens to rocket engines when you change the thrust levels. Normally, rocket engines like to work in a fairly narrow thrust range, and we've learned a lot through this project. And Pratt & Whitney Rocketdyne down in West Palm Beach, Florida, have been working on that for us. Now, of course, once you get to the moon, you have to have a very robust extravehicular activity and surface mobility capability. And we have, of course, been, Joe Cosmo at Johnson Space Center has had his lunar analog activity, the Desert Rats, going for a number of years. We expanded that last summer to bring in some of our robots. And so this is a picture of our human and his robotic friends. Now, these robots will probably not be the kind of robots that show up on the moon, but the capabilities that they represent will probably be there to help us to establish this lunar outpost. This robot was built by the JPL team. It's called the Athlete. The same folks that developed the Mars exploration rovers developed this, and it's a kneeling robot that can carry structures such as this EVA recharge facility. This robot can walk as well as roll, and also has the capability to use tools. So you could emplace structures using this robot. Of course, we have our JSC, this is the Robonaut, but we put Robonaut on wheels, so we call him the Centaur now, and it's a dexterous robot. We have a little inspection robot called the K-10. It's kind of like the R2-D2 from the Star Wars movies. And then we have the Scout rover, which is more than a rover. It's actually a robot as well. Can operate autonomously and telerobotically. And then, of course, we have a number of new spacesuit concepts that we're looking at that will increase the work efficiency and increase the ability of the astronaut to move around, the flexibility and dexterity of the astronaut. I'll talk a little bit about closed-loop life support, and as I get into this part, this is where the space station will really help us out. I had to put a picture of me in there, and these cans are actually cans of wastewater. They're urine, and right now, we don't have a way to recycle that. But we hope to deploy the closed-loop system soon to demonstrate a capability to recover this liquid, reducing the amount of upmass that we need for consumables, and eventually take these kinds of technologies and bring those to the lunar outpost as well, because it's even more expensive to bring those kinds of supplies to the lunar surface. So the space station will be the location where we try out some of these closed-loop systems. And of course, on the Russian side, we have the the SRVK, which helps us to recycle the humidity from the space station. So we're very successful there, and then this will make it even more so as we continue to close that loop. Talked a little bit about in situ resource production and utilization. And we have a number of projects, some of them international, looking at different drilling capabilities, different pilot systems that can take the regolith and get oxygen from that regolith. Also, if we are able to locate water ice and permanently shadowed craters, we may be able to tap that resource as well to give us water that we could use either for makeup water for human consumption, or potentially to make hydrogen and oxygen for rocket fuel. Now, to understand to be better ready to explore the lunar surface, we have to understand the effects of the lunar environment on human performance. And we have a very ambitious project in our human research program to look at how we can understand the physiology of EVA crew members. And this is a rig where we have an astronaut in one of the new suits on a treadmill with a weight relief, and we're trying to understand the metabolics of having to do that walk back if the rover for some reason broke down away from the outpost. So we're doing this to understand. We're doing it both in the 1/6 G of the moon, and we're also looking at the lunar or the Mars case as well. And we found some very interesting effects as you go from the 1/6 to the 3/8 G. Remote healthcare systems, very important, again, to keeping us happy and healthy and productive. And again, the space station is a great place for us to test out technologies like this. And so we have Gennady Padalka using that ultrasound on Mike Fink, who we saw earlier today. And it's just a great capability, and the space station affords us the opportunity to really test out these technologies and to see how we can make them better and get them ready for our trips to the moon. Other things that we're looking at, new lighting systems using LED lights, the light-emitting diodes. We hope to fly some of those in the next, I think, 2 shuttle flights from now. Now, we talked a little bit about the human missions, but before the human missions, we have some robotic precursor missions. And the Lunar Reconnaissance Orbiter is the one that we have getting ready for launch in 2008. It's being built out at the Goddard Space Flight Center, and it's well on its way to development. And what you see below are the instruments that have been manifested with this satellite. It is an orbiter. It will orbit at 50 kilometers above the lunar surface. And it will provide very detailed topographical information. It has the Lunar Reconnaissance Orbiter camera, the LROC, and along with the LOLA, the Lunar Orbiter Laser Altimeter, will provide high-resolution imagery and altimetry. In addition, we have the LEND instrument, which is coming from Russia. It's the Lunar Exploration Neutron Detector. Again, looking for neutrons that could indicate the presence of hydrogen. We have the Diviner Lunar Radiometer Experiment looking at temperature gradients. The Crater, the Cosmic Ray Telescope for effects of radiation. Again, looking at the radiation environment in lunar orbit and how knowing that will help us to better plan our shielding strategies. Mini-RF, which is a synthetic aperture array radar. It will operate in 2 frequency bands, and we hope to use that, again, for mapping and for detection of lunar resources. And then the LAMP, the Lyman Alpha mapping, Lyman Alpha mapping project. And I just call it LAMP. But it's, again, looking for signs of hydrogen that may be signs of water ice. Now, the Lunar Reconnaissance Orbiter will enable global maps. When we flew during the Apollo program, we had a number of lunar precursors, and they mapped the areas around the equatorial part, well, actually, of the near side of the moon. With the Lunar Reconnaissance Orbiter, we will be able to, from a polar orbit, map the entire sphere of the moon, and then also we have identified a number of landing site areas, and we're going to get additional data on those areas, both on the front side and the back side of the moon. So we'll have a complete picture of the moon when the Lunar Reconnaissance Orbiter is complete. Now, one of the places of interest are some of the polar craters, specifically in the South Pole. Shackleton has been identified as one of high interest because it has areas of near continuous illumination, both winter and summer. And so if this is an area that we are very interested in, we are also planning to investigate whether there's water ice in this crater or in craters near this area. So the Shackleton's one we're keeping our eye on. Now what I'd like to do is to run the video of our Lunar Reconnaissance Orbiter and L-Cross mission. I haven't talked about L-Cross, but once the Lunar Reconnaissance Orbiter is, well, the story goes back to when Scott Horowitz came on board as associate administrator. Goddard had begun design of the Lunar Reconnaissance Orbiter. It's a liquid-fueled going out to the moon. And we had a Delta II rocket which spins the satellite. And there was concern about an instability when you spin a liquid-fueled satellite. And so we decided to transfer the Lunar Reconnaissance Orbiter to one of our larger rockets, an EELV, an Atlas V. And with an Atlas V, we had additional capability to send an additional satellite to the moon. So the L-Cross was born, the Lunar Crater Observation and Sensing Satellite. Its job will be to direct the upper stage from the Atlas into a crater, a permanently shadowed crater, and then observe the plume that comes out to look for signs of water ice. The this L-Cross shepherding spacecraft then, once it has observed the impact, will itself impact the moon and be observed from the Earth. And so you'll see that in this little video here. It all starts at the Cape. So this will be an Atlas V. So the upper stage of the Atlas V, the Centaur, will then send the Lunar Reconnaissance Orbiter and the L-Cross spacecraft away from Earth toward the moon. Of course, you see the Lunar Reconnaissance Orbiter moving out on its way to achieve orbit around the moon. And it'll be a series of maneuvers as it gets to the moon and lowers its orbit down to that 50-kilometer orbit, which is pretty low. Now this depicts the trajectory of the Centaur and the L-Cross spacecraft. The Centaur is a LOX hydrogen spacecraft, and that time, it's about 2 months, and during that time, the LOX and hydrogen should vent out from the tanks of the Centaur. So it should not have hydrogen and oxygen on board. Now the L-cross will then separate once it's lined up the Centaur for its impact. So that was the impact there of the Centaur. And you can see now the L-cross satellite flying through the plume has a number of instruments, again looking for spectrum that are indicative of water ice. Then it will also impact, producing a plume that can be seen from the Earth. And also can be seen from the Lunar Reconnaissance Orbiter as well. And so, as you can see from my talk, we have a lot of ambitious plans out there. We have a lot of work underway already. We hope to engage our international partners in this enterprise, and we hope to leverage off of the work we're doing on the International Space Station as well. So we're very excited about this, and we hope y'all will be able to support us and get us back to the moon and beyond. So thank you. And I'd be happy to entertain questions. Absolutely, sir.
Apollo-era engines. Why does it take so long?
Well, it turns out that the J2 engine has not flown in a long time, and so we are asking it to do things that it didn't do before back in the Apollo era. So what you find, when you have a big break in production is you have to do a lot of work to requalify things and also to retest things. And so it just takes a long time. A lot of the industrial capacity we found out has gone away, or it's there, but it takes a long time. Engine valves, for example, can take years to procure. So there's some long lead time there. It's hard to believe, but some of these are the realities of buying these unique parts. So what we hope to do by picking the J2, by using RS-68s, is to develop a production line. So we're buying a number of these engines, and so we get a production line going, and we get some economies of scale. So there's again, the idea is to try to look for ways up front to lower the overall cost, the life cycle cost of these vehicles. But the robotics, if we're successful in deploying intelligent robotics to assist the human explorers, that will certainly be a new twist as well. And the interaction of the humans and the robots will be, I think, one of the issues that this group will have to deal with, and it has to do with cognition, mobile agents, and how we control these kinds of things. It may start off with one robot, eventually could burgeon to many more. Sure, please.
One of your slides mentioned the potential for a lunar human resource laboratory. You talked about the potential for having a laboratory on the moon to learn about the human existence in the lunar environment. You recall that?
Well, it was to understand. Well, I think there's to understand the effects of the overall lunar environment on humans, right, some of which we would do before. I would anticipate that there would be opportunities while we're on the surface to do science to understand what the effect of the 1,6-G is. Do you get back your your muscle mass, your bone mass? Will 1,6-G sustain you? So those are things that questions that we'll be able to answer while we're there. So I think we're in the beginning stages of trying to do some planning in that regard. But I think those opportunities will be there, and we'll need to take advantage of them.
Thank you.
Carl, what are the implications for planning future missions if we're really fortunate and we hit a high load of hydrogen in Shackleton's crater?
Well, I think that really, if we're able to find water ice and successfully extract it from the crater, that really opens up a lot of opportunities to be able to bring more things to the surface with the knowledge that you have the propellant to get back. And so all of a sudden you don't have to carry all that extra return propellant down. So it really opens things up as far as what we can do on the moon. So and then of course there's the opportunities, just make up life support, water and oxygen and such.
Carl, if I understand your response to Larry Young, it seems as though what you're going to do is use the moon surface as a lab to find out if you can produce a countermeasure through EVA without any other option to have a countermeasure process going on as part of the equation.
Well, I think I think you're reading a little more into my my thoughts here.
I didn't hear any comments in your talk about what modalities might be available to help the astronaut maintain physiological homeostasis as part of the mission objective on the moon outpost, only that you would take advantage of the EVA opportunity to learn if that is going to be a suitable way in which to maintain physiological homeostasis. So basically you're flying by the seat of your pants.
Well, I think first of all, just being in a 1/6 gravity environment there will be information gathered there as far as, does that 1/6G help you? Is it different than what we see in 0G? The EVAs, where you're wearing, what we hope is not that heavy a suit, and the extravehicular activities should also provide a countermeasure capability. We don't know if that'll be enough or not. And so I think there's going to be opportunities there for analysis of the data. As far as exercise modalities, those are good questions. I think if we have a long-term outpost, there would have to be modalities for maintaining muscle, circulatory, aerobic capability. So I think you could expect that. We haven't gotten that far yet. So, but I would anticipate that we would develop those kinds of things. Exactly what kinds of things, whether it would be a treadmill or a bike or some other device. Certainly, I think there's a lot of options out there, but we haven't gotten that far yet. Go ahead, Chuck. Oh.
One question I think we all get a lot is what is the U.S. science agenda on the station? Obviously, things changed a lot when the VSE came in. Is there a new plan that we can refer to answer those kinds of questions? Certainly we were all hoping that there'd be a lot of human subjects available and an opportunity to do human research at least through 2016. Can you give us an update on, what is the new plan and how far into time does it extend?
Well, right now, we through the Human Research Program, is Kathy still here? No, Kathy. Okay. Well, Kathy Lorini and Dennis Grounds have put together the Human Research Program. A part of that is the ISS Medical Project, and they have developed a roadmap out to 2016 with investigations, and in addition, they have ground investigations as well. So that they're pulling that story together right now. And I think they're working very closely with NSBRI to make sure that we have all the gaps filled. And part of the whole rollout of that plan was the development of this risk analysis and the standards. So given that, looking at the evidence, finding where the holes are, and then filling in with the research.
What about the other disciplines? Are the plans complete there?
As far as the some more of the fundamental life sciences, not
just life sciences, but
the physical sciences. We, of course, everything shrunk down, but we still have a physical science program, primarily fluids and combustion. We hope to launch the combustion integrated rack, the fluids integrated rack, in 2008 and 2009. We have a material science rack that will be going up probably in 2009 as well. And so we plan to utilize those on orbit. We still have a cadre of PIs. We also have some of the fundamental work. In the 2005 NASA Authorization Act, there was a set aside for more fundamentally based research, and so we have some life science and some microgravity science in there as well, and so those plans are fairly well laid out as well.
Is there a place we can go to see the details yet? Or is that...
We're putting that together. You sound like some of the congressional staffers. Where's your plan? So we're pulling that together, and we hope to get that out. So the integrated plan, both for the human research element and then for these the physical science and the fundamental life science. So it's coming.
We've been talking a lot about partnership, collaboration. And right now, under the NASA leadership, 14 countries are involved in developing the global exploration strategy. But what beyond this? Have there been thought about how partners will get involved? Is it going to be an invitation? Is it going to be potential countries will present business plans, so to speak, will be reviewed and accepted or rejected? Have we thought about the process of how the partnership will be developed?
Well, I think to answer your question, and I have not been closely connected with the global exploration strategy. I've been involved in the partnerships that we have existing with ISIL-SWIG, with our joint working group with our Russian partners, with the we have an international advanced life support working group, and so we've continued those collaborations a little bit on the microgravity sciences as well. From the global exploration strategy, we've come up with sort of a framework, but we're still working to get all the 14 countries on board with that and signed up with this framework of how we do business. So that's still a piece that's in work right now. So I wish I could give you more details on that, but it is our external relations group, international group, is working that even as we speak. Any other questions? All right. Thank you.